Swayam Prabha. Digital India. Educated India.
But let's look at a related problem which is in your problem sheet. I don't know how many people really tried, which is a subgraph isomorphism problem. What is a subgraph isomorphism problem? Your input is two graphs G and H, and the question is there a subgraph of G isomorphic to H? Okay, so and if I ask you, this is my H, and if this is my G, and I ask, is there a subgraph of G which is isomorphic to H, and is the answer yes or no here? Yes, right, because you can map this, there is a copy of this sitting inside here, right. So, what it means is you are allowed to delete vertices and edges from your graph G. Now, the resulting two graphs must be isomorphic. So, you should be able to have a function which maps. So, I can map this to 1, this is 2, and this is 3 and 4, right. Now, this problem is NP complete. Testing whether two graphs are isomorphic is, we do not know, but is there a copy of H sitting inside G is NP complete. Okay, how do we show it as an NP? Right, I have this graph G and I have this H, and I claim that there is H is sitting inside G. Suppose the answer is yes, what would be a proof that will convince me that there is a copy of H inside G? You have to give two things, very good. You have to give the subgraph. So, you give a subset of vertices here, that will be your witness. In addition, you also give a function, okay, this is my 1, this is my 2, this is my 3. Then all I just verify is that in this subgraph, these two are isomorphic. Okay. So, in NP, the certificate would be subgraph of G and the bijection, the isomorphism between H and the subgraph. How do you show it as NP hard? Reduction from Hamiltonian cycle. Okay. How do we show reduction? We start from the Hamiltonian cycle problem to subgraph isomorphism. I want to give a reduction. How do we do reduction? Start with an input for the Hamiltonian cycle problem. What is the input? Some graph is given. What is the input for a subgraph isomorphism? Two graphs. Right, subgraph isomorphism problem requires two graphs. So, what are the two graphs? What are the two graphs you are going to give? G and what is H here? Cycle on n vertices. I have to produce G and H from this G, right? That is the function. You are mapping from this G a G and a H. So, the same G I am going to use for this here, and what is my H? A cycle on n vertices. That's exactly what you said. I don't know why you don't see it as a reduction, right? And my H would be simply a cycle on n vertices. Now, if G has a Hamiltonian cycle, then this copy of H sits in G. That's exactly the definition. And if there is a copy of H in G, G has a Hamiltonian cycle. Can you think of another problem to reduce from? We've seen a lot of examples today, not today, in the last couple of days, where in G you are trying to find something. Click, right? So, reduction from click. What is the problem here? So, let's okay, where do I erase it? Let's take a new page. Okay, so I'm going to reduce from click to subgraph isomorphism problem. Let's go through the template slowly. What is the input for the click problem? G and K. There is a graph G, K. I want to know whether there is a click of size K in the graph G. How do I translate it into input for subgraph isomorphism? G and a click on K vertices. I create it. This is my H. Now I ask, is this sitting inside G? This is exactly. So if you think about it, subgraph isomorphism is a generalization of click, Hamiltonian cycle. What other problem you can think of? You've seen independent set, right? Independent set problem is given a graph, are there K vertices that form an independent set? So you take GK and G and this, what would be my H? Null graph on K vertices, null, an edgeless graph on K vertices, and I ask, is there a copy of this sitting inside G? That's exact. So subgraph isomorphism is actually a generalization of click, independent set, Hamiltonian cycle problems, right? Since these special cases are hard, the generalization will be hard. So was that a hard problem? You guys didn't do it in your problem sheet, right? Reduction from click, reduction from Hamiltonian cycle, you have so many choices here. So subgraph isomorphism is NP hard, okay? Good. I think that's all the examples I'm going to do. Now I want to tell you what next, okay? So a problem is NP complete. Means what? Well, we don't expect a polynomial time algorithm, which is what an efficient algorithm is, which will work on all input instances and give you the correct answer all the time on general graphs, right? That's what I expect. The problem needs to be solved. The problem doesn't go away. So what do we do with it, right? So dealing with this will be the topic for the rest of this week and next week on the algorithms things, right? Once a problem is NP complete, what do we do with it? Okay. Well, there are a lot of approaches. First, what does it mean? A problem is NP complete means that the most general instances of the problem you don't expect to solve exactly in polynomial time, right? Okay. Maybe some special instances you can solve. In polynomial time. Have you seen examples of this? Vertex cover in bipartite graph. Even though vertex cover in general graph is NP hard, vertex cover in bipartite graph is polynomial time solvable. What about maximum independent set in bipartite graphs? Yes, S minus whatever, right? In any graph, you take a minimum vertex cover, look at its complement, that's a maximum independent set. So if I can find minimum vertex cover in polynomial time, I can also find maximum independent set in that graph in polynomial time, because take that graph, apply your Koenig's theorem to get your maximum matching and hence minimum vertex cover. Take the complement of the minimum vertex cover, you get maximum independence. Right? What about max click in bipartite graphs? Can you solve it in polynomial time? One idea is you can take the complement of the graph and solve independent set. That's what we did. But what's the problem? Complement may not be bipartite, right? So I can't, because I know I can solve independent set in bipartite graphs, but if I take the complement of this and try and find independent set, then I can't find, that may not be bipartite. Can you have a larger click in bipartite graphs? Can you have a triangle in bipartite graph? Because bipartite graphs don't have odd cycles. If you can't even have triangle, how can you have even larger clicks? Right? Any large click will have a triangle sitting inside. So you can't have large clicks at all in bipartite graphs. The max click possible, if there is an edge at all, is 2, otherwise 1. Right? So trivial. You don't need any big machinery of Koenig's theorem or taking complement or anything. Okay. So the point I wanted to mention here is that you don't get scared when the problem is NP complete, because maybe you have some special structure in the problem which you can exploit, right. So it's completely trivial. Just see if there is an edge and give that, and that's a max click possible, because there are no odd cycles, no triangles possible, no larger clicks possible. So this is one big theme in this area of special instances, and you will see a lot of it next week. So for example, in one of the evening lectures, you saw something about interval graphs, right? Somehow graph modeling time intervals. So there are so we have seen some special graphs, bipartite graphs. Planar graphs is one special class of graphs where many of these problems can be studied. Some of these problems are NP hard even in planar graphs, some are polynomial time solvable. Caudal graphs, comparability graphs, perfect graphs, these are a lot of such graphs, special instances. 2SAT, one of the problem in your problem sheet is that the general SAT is NP complete, 3SAT is NP complete, but if I tell you that every clause has at most 2 variables, you can solve it in polynomial time. So the game here is to exploit some structure in the input and somehow design polynomial time algorithm, or maybe show that it is NP hard also even on that special instance. That will be a strong result. So this is one way. So this is, each one is a big research area. There are specialized books written on each of these topics. Okay, there is so much to cover. Another direction is approximation algorithm, which I'll start from in the next lecture. You've already seen some examples in your problem sheet probably. So this is a very natural thing, right? I mean, I think many people were discussing with me, oh, why is it TSP so hard? I go from here and I go here and can I not get some tour of some cost? Yes, you will get some tour of some cost, and it won't be optimum, but that's okay. Anyway, I want to solve it in polynomial time, so do I really care if it's not optimum? But I want to make sure it is not too far from the optimum, right? So here the challenge is we will actually analyze the quality of the solution. This is a challenge, not so much the running time, because the algorithms will be simple, there will be polynomial time algorithms, but we will produce some solution. The real theoretical work here is to actually look at the solution and compare it with the optimum and see how far they will be optimum. Okay. Now this is a challenge because I don't know how to compute the optimum, because the optimum computation is an NP hard problem, but we will use some bounds and we will try and argue and come up with the quality, how close to the optimum the solution is. Okay, so this is the big challenge. There are books, at least 2-3 books on whole area of approximation algorithms. Okay. Now, often in engineering sciences, many sciences, they do face huge problems in VLSI, various kind of problems which are typically NP hard. They try some heuristics and get some solution. Okay, I'm usually satisfied with it, or try it on some benchmark problems. There will be some benchmark solutions you can compare. But in theory, we want to just compare the quality. We want to look at the solution and see how far or how close to the optimum it is. Okay, that is what would complete the picture of understanding of the algorithm for that problem. The other area we will look at parameterized algorithms. So, here the idea is we know that, let us say, minimum vertex cover is polynomial time solvable in bipartite graphs. Suppose I have a graph which is sort of close to bipartite, right. So, there is some, what do you mean by close to? So, we will associate some parameter with the input. And then you ask some small parameter, and I am willing to be exponential on the small parameter, but the rest of it should be polynomial time, right. So, let us say some k is the parameter associated with the input, and I want an algorithm which is maybe 2 power k plus n cubed or something like that. So, typically our problems in this area will come with some parameter. Now, parameters are plenty in your input, right. It is not, input size need not be the only thing to measure. It's, think of it as a multi-dimensional framework where we are trying to design algorithms looking at various parameters in your input, and in particular if there is some small parameter, I am willing to be exponential on that parameter, but I want to be polynomial in the remaining rest of the input. That would still be a feasible algorithm. Okay. So, this will be a whole set of things which we will look at next week on parameterized algorithms. And briefly we will also look at because these two are somewhat related. So, here for example, so I want to solve the problem exactly, no approximations. So, I know the problem is NP hard, so I have to live with the exponential time algorithm, but in the exponential world there are grades of running time, right. There is n factorial, there is 2 power n, there is 1.3 power n, there is 2 power square root of n, all of these are non-polynomial, okay. But 2 power square root of n would be better than 2 power n, 2 power n would be better than n factorial, 1.3 power n would be better than 2 power n. So, I live in the exponential world, I know that these problems are hard, so I have to get only exponential algorithm, but can I get a better exponential algorithm? Okay. So, this is the area of work in exact exponential algorithm. Okay. So, in the rest of this week and next week, in this theme of algorithms, we will see a lot of algorithms in each of this domain. Okay. This in the last 20-30 years, this PNP conjecture has opened up all of these avenues of research. So, these are, we're getting into some frontiers of work in algorithms. So, here, as I said, you will easily come up with many algorithms, heuristics for many of these hard problems, but challenge is I look at a solution and see how good it is compared to the optimum. Okay, and that is where we will spend all our time on. Okay, so let us look at the minimum vertex cover problem. Right. So, I have a graph and I want a subset of vertices that cover all edges. So, what would be a natural greedy algorithm? Pick the vertex with highest degree, include it in your solution, delete that vertex and repeat. Right. This is a natural greedy algorithm. I don't know whether we have it in a problem sheet yet, that this does not necessarily produce the optimum solution. Okay. So, here is a simple example. Okay. So, let us say so, what would your algorithm do? It will pick V into the solution first, and then once you pick V, there are some 10 vertices left. How many vertices you need? How many more you need? 5 more you need, right? But if you think about it, that 5 more is enough too. You don't need V at all, right? If I pick 9, 7, 5, 3, 1, I will cover all edges. Okay. Now, this is not really a bad example. I am just producing like one extra, but there are examples we will see that the solution produced by this algorithm can be very bad, more than any constant ratio compared to an optimum solution. Okay. You saw the coloring example, right, yesterday in the problem sheet, where the optimum is 2, but right, let's go through that example, right. So, recall the greedy coloring algorithm. So, I have start with an arbitrary ordering, let us say V1, V2, Vn, color V1 with color 1, and then I say for I equal to 2 to n, color Vi with the smallest possible color. And you've seen a lot of greedy examples which they don't produce optimum, but I want to show you that not just they don't produce optimum, it can be pretty bad. Okay. Maybe you've seen this yesterday, but let me do it again. So the algorithm is simple. It will definitely produce a proper coloring, right. So, what do I mean by smallest possible color? I take a new vertex and then see look at all its neighbors. I can't use that color, any of those colors. Choose a color which is free available, but not any of the colors of my neighbors which have been colored. Just color it, right. That's a greedy algorithm, and at the end of it, it will produce a proper coloring. It will produce some number of colors, but let's see what it will do on this. I mean this. Suppose this is my bipartite graph where I have, this is my ordering and all edges are there except these edges. Okay. These edges are missing, but every possible edge is there otherwise. Okay. So, bipartite graph. So, how many colors do you need? 2 colors are enough, right. But if you follow this greedy algorithm, what will it do? It will color this guy 1, it will start with that. Since 2 is not adjacent to 1, I can give color 1, because the smallest possible colors 2 will get 1. Then I get to 3, 3 is adjacent to this color, because it is a complete bipartite graph except a matching, right. So, all these edges are there. So, since 3 is adjacent to this guy and it has been already colored 1, so I have to use a separate color. So, I will color it 2. Then I come to 4, 4 is adjacent to 1, so I can't use color 1, 4 is adjacent to 3, it is not adjacent to 3, so I can use color 2. Then I come to 5, 5 is adjacent to 2 and 4, so 1 and color 2 colors are ruled out, so I have to give color 3. When I come to 6, 6 is adjacent to 1 and 3. So, colors 1 and 2 are ruled out, but it is not adjacent to 5. So, I get 3. And you see that I can just go on adding this. So, if the graph has 10,000 vertices on each side, I will use some 10,000 colors, whereas 2 is sufficient, right. So, not only this is not optimal, this is so far away from the optimum. Okay. So, that is the measure. We want to see how far away from the optimum. So, in particular, this greedy algorithm produces a solution which we can prove. We will do maybe tomorrow. That is at most some log n times optimum. This is the quality of the solution which we will show tomorrow. Okay, but it can be as bad. That also we will see later. But I will give you a simpler algorithm for vertex cover. So, remember this ratio is what I am interested in, right. It is going to produce a solution which is clearly greater than optimum, but I do not want it to be too far away from the optimum. So, if I say that it is, if the optimum is 10, this will be at most 20, then it is a reasonable algorithm, it is a reasonable approximate algorithm. And here is a simple 2 approximation algorithm. Yeah. So, how is log n ratio? I have not proved it, we will do it tomorrow. Okay. In fact, we will do it for a more general case, and not only at most log n, there are examples for which it can be as bad. Okay. So, here is my algorithm. Find a maximum matching in the graph. It is a bipartite graph, we know how to find maximum matching using flows, but even on general graphs you can find maximum matching. There is a more complicated algorithm, but in polynomial time you can find a maximum matching. Okay. Let us call that matching as M. Output S is equal to both endpoints of all edges of M. That is it. This is my algorithm. Find a maximum matching, pick both endpoints of every matching edge and output that. Okay. So, let us call this output as S. So, is the algorithm clear? So, if I have a graph like this, so I will first find a maximum matching here. Say this is a matching, this is a matching. Okay, so let us call this 1, 2. Is that a maximum matching? But at least I can't increase this matching. Maybe there is a larger matching. Actually, there is a larger matching, but it's useful to use this also. I'll prove a point here. Okay. So, this is not maximum matching because this matching size is 2, but instead I can have 1, 4, 5, 6, 2, 3 as another maximum matching, but even this matching is good enough for me. So, I do not really need maximum matching, I need something else, I will write that later. So, now my output is the both endpoints 1, 2, 4, 6. Okay, so what is it? It is actually a maximal matching, not necessarily maximum matching, but a maximal matching. Maximal matching, what is maximal matching? You can't add anymore. This may not be of the maximum cardinality, but this matching cannot be extended. A maximum matching is clearly a maximal matching, but a maximal matching need not be a maximum matching. Here is an example. A maximal matching is very easy to find. Why? How do I find it? Just a greedy algorithm. I take an edge, put it in my solution, delete all edges which share endpoints with this, go and find another edge. Keep doing this. What I get is a maximal matching. Okay, this is much easier than applying Koenig's algorithm, doing anything more sophisticated. Maximal matching. Now, this is my output. I have to make two claims now. One, S is a vertex cover. My claim 2 is cardinality of S always is at most 2 times optimum. Let us try and prove each of this. Okay. Is it clear why S is a vertex cover? If S is not if S does not, the endpoints of these matching does not cover all edges, I mean there is some other edge left. Why did you not add it to your maximal matching? Maximal matching means I would have added to my maximal matching. The fact that it is a maximal matching means that this matching could not be extended. So, there is no more edge completely outside. So, these endpoints cover all edges, right. So, proof of claim 1, if S does not cover some edge xy, then M can be extended to M union xy, contradicting M is maximal. Okay, claim 2. My size of S is at most 2 times opt. What is opt? Size of minimum vertex cover, right? That the solution I have produced, it may not be optimum, but it is never more than twice the optimum. Why is this? Because M is a matching. What do we know about connection between minimum vertex cover and size of a matching? Minimum vertex cover is greater than or equal to size of a matching. Is greater than or equal to size of any matching. Why? Because matching is a collection of disjoint edges. Each edge needs to be covered. So, you need to pick at least one from each of the edges, and one vertex will not cover other edges because these are disjoint. So, each vertex will cover only that edge. It may cover a lot of edges, other edges not in the matching, but for edges in the matching you need at least one from each of the edges. So, minimum vertex cover size is at least M, but what is S? How did we get S? We picked both endpoints of our matching. So, S is exactly 2 times M, right. So, does not it follow that this is less than or equal to 2 times size of minimum vertex? So, what I have produced is a ratio 2 approximation algorithm for vertex cover, right. This is sort of counterintuitive. The greedy algorithm, which seems very natural, actually does not have a constant ratio, any constant ratio. You can come up with examples. Whereas this is slightly counterintuitive. You pick an edge and pick both endpoints into my solution and find a maximal matching and do this for every edge. That together form a vertex cover and whose value is at most twice the optimum. Okay. So, the goal in this area, right, generally in algorithms we are trying to improve the running time of the algorithm. Here you want to improve this approximation ratio. How close to the optimum can you get, right? Now, this is the best known ratio. Improving the approximation ratio for minimum vertex cover beyond 2 is a famous open problem, and it is believed again, like the P not equal to NP conjecture, that you cannot do better than 2 unless some collapse happens, right. If P is equal to NP, then you can actually find the minimum vertex cover. So, you can make it 1, But if P is not equal to NP or under some other conjectures, it is believed that you can't improve the ratio to beyond 2.